Hey, Steve, how are you?
Hello, how are you doing?
Doing well.
Okay, you can hear me okay?
I can hear you. I'm getting a little bit of echo from your audio, but not a big deal from my perspective.
Oh, that's so strange. Is this any better?
No, that was actually, I have a tendency as a moderator to open a second window, so I just fixed it.
Okay. So it's actually just you.
Yeah, user error. I'm trying with 5 minutes of passing time. I'm trying to like reorganize myself in between sessions in like a 5-minute window. So just trying to click on all of the stuff and wait for it to open. All right, and here we have Nate.
Work?
Yeah, there you are.
Yes.
Can you hear me?
Yes, you can.
First try.
There you go.
Okay.
You see these practice runs pay off.
Yeah.
Paying off.
How's it going, Patrick? How's the first round?
It's pretty good. So this is the third session. It's been an interesting morning. It's like, I think a lot of it is just kind of adapting to the platform and even from the point of view of an attendee, even if this is not your first virtual conference, if it's like your first one using Hopin, then things are just different. It's not like the usual cattle call for everybody to file out of a ballroom and then wander down the hallway and find something that looks nice. But it would be nicer if we could grab coffee in the hallway. That would make things go a little better for me. But grand scheme of things, it's not a big deal. So
Yeah. David's asking if we will still be doing Cisco minions. I wonder who the friend is.
Only if you make them, David.
Yeah, you have to build it.
Because then we know we can rely on them.
What's up, Jason? I was looking for my Saul hat. I don't have it.
He had it the other day, so I know it exists.
Yeah.
You're fine. You thought there was going to be an amazing revelation, David, about the progress of Cisco minions?
No.
No? Okay. Yes, we did change the title.
Mm-hmm.
Are you going to jump on to set the record straight there? Oh, what happened to you?
Double David.
Double.
That's amazing.
Hey, double diamond works better. So that's why I was wondering what happened to the Cisco minions.
I don't.
Yeah, we unmade them.
Yeah.
Are you telling me there's a Cisco minion in my future?
I don't want to. It's as a marketing event, I can't guarantee that.
Okay. I did have them at unit test.
There you go. I mean, so they do exist somewhere in a flight of fancy, but today we will concentrate on more of the containerization and deployment at scale.
Right.
You start.
Yeah.
Nate?
Cool. Let me make sure I can share.
I think I'll share my part later on. That way we don't have to ask each other to click next.
I can't specifically share PowerPoint, but how's this look? Can you see it?
Yeah. So I still see Saeed's as well, and so this is where we'll just kind of there you go. That totally works.
Yeah. Cool. Yeah, I wish I could see the chat and stuff, but I got this all taken up, so.
That's fine. So in my experience so far, I'll have enough bandwidth to kind of call out any of those things, and by all means, I can interrupt if necessary. And,
Yeah, no, definitely. That'd be great. If we have any interesting questions, just butt in and say something. I'd like to have I'd like it for it to be a discussion. If anything interesting comes up, and if we have cool questions, we can definitely make time for stopping and talking about that. But just to get started, I'm Nathan Rogers, network automation engineer at IBM, and I'm with Saeed here. And you want to say something, Saeed?
Saeed van Klundert, network automation engineer at IBM.
Sweet. Yeah, so go ahead.
That's fine. So just to give everybody a little bit of background so that I can claim that I did my job as a moderator, to give everybody a little picture of IBM's use case here, their effort is centered around IBM Cloud's back-end network infrastructure management. And so their goal is to handle any of the typical day-to-day configuration drift, as well as delivery of SALT tasks and jobs to other teams like the network reliability engineering teams, as well as handle some of the more complex things like orchestrating, at least close to full uptime availability across firmware updates for AB pairs and things of that nature. And so they're doing this across, what do you guys at 29 different data centers and about 75,000 network minions that they're currently working on exerting control over using SALT. And so I will leave that as the intro and you guys can carry on. Thanks, guys.
Sweet. Yeah, thanks so much, Patrick. I think it's quite a bit more than 29 data centers, but the 75K minions is a pretty accurate number. And that's how many we actually have SALT minions for. So that's kind of one of the main topics of this talk is that how do you do that at scale, right? And so there's a couple interesting things about our deployment of SALT is that it's primarily focused on orchestrating the network devices, and also that it's containerized. Every SALT master that we run is running in a Docker container. And so, I mean, if you guys are, if anyone's looking to get insight on how to scale their deployment, or you get into Dockerization of your SALT masters, or specifically work with network devices, hopefully we have some insight as far as how we've managed to do that. So that's and so some of the benefits that we see, and we have.
I don't see any slides actually.
You don't see a slide?
No.
Do you see a slide, Patrick?
I see a stable Chrome tab that has the current session. You might have to reshare.
Yeah, maybe I can't full screen it. I can share just the PowerPoint. How's this work?
There you go. That's good to me.
Oh, sweet.
Yes.
Now I can see the rest of the stuff too. That's way better. I can see the chat too. Anyway. Play this. Oh, no, I can't full screen it.
Yeah, it looks good now.
Well, at
See
least
the
you'll see it.
presentation though. Awesome.
Yeah, so this was us, just in case you missed it. But I wanted to talk about the benefits that we'd see from doing from orchestrating our platform this way and setting it up like this is with every SALT master that we have running in a Docker container, that really streamlines the upgrade process. And I'm talking things like, I mean, even down to like a Python package. If you want to pip install something, like you don't have to worry about other dependencies on the bare metal or anything like that. And as far as updating SALT, we just update the Docker file that builds that container, and it's an easy process to redeploy everything. What I put for split up the minion load between masters. I mean, we just found it way more efficient to say, like, if we have 2,500 minions we want to assign to a server, it was way more efficient and performant for us to split those up into 500 minions over 5 containers and have 500 minions talking to over one event bus to one master, 16 threads, versus just trying to load up one master with the 2,500 minions in a proxy fashion, at least. So there was some performance stuff there. But of course, you reduce your dependence on hardware as well. I mean, we can move containers around, move them to different data centers, replace hardware without any downtime in that way. And really interesting is our CI workflow too. So we basically, the Docker container that we use that runs SALT is just a blank slate. It's got a SALT master and minion, and then we clone our code repo into it. And so it's really easy to just start up a container in our dev environment and have a blank slate where you then run code and do some configurations against test minions. And like that's kind of a Jenkins thing, and that's before we ever merge any code into our master repo. It goes through that process. So it's just it made that process really streamlined and efficient. So, and then I'm going to talk about mostly the containerized platform kind of deployment and how that looks first, and then later Saeed will get into the benefits of running the SALT minion locally on the devices, so like on box native minion type stuff and the performance advantages in that, and kind of also what we do specifically network-wise, how we interact with the devices and use the Minion to gather data and configure them. So I'm going to set this up by kind of describing the platform architecture that we have. And so what this is at the top is it's a container. It's called the master of the universe. So it's the top level orchestration master that controls the set of minions that are doing not the network functions, but the server deployment functions. So it's just one salt master, and we have minions in each of our salt servers that are going to report up to that master, and then it has a local minion as well. And that becomes interesting when we look at kind of the second level. We gotta have like a two-tiered layer of salt masters and minions. So this next level is all containers inside the servers, and those salt masters in the servers are what network devices are actually going to report up to. So we have this first tier, I guess, salt master layer, and then and all the network devices are reporting up to those, and they're all in containers. And then in order to orchestrate and deploy those containers, we utilize salt minions that are reporting up to the top tier master layer. And so this is scaled out. We got 150, I think, containers deployed right now to manage the 75,000 devices. So this is wildly scaled, and it's kind of the logical architecture of that. So this is like the top level. This is what we saw in the previous slide. So this is the top level master of the universe container that's orchestrating both minions on servers and minions in containers. And the minions in the containers are orchestrating the proxy native minions that are the network devices. I guess the reason I want to talk about also the deployment not only of, it's kind of an A to Z thing that we're going to discuss here, and it's from just having nothing, really having just servers and basically being here, where you just have minions on servers. How do we get from that to having masters that control all 75,000 devices without having to program them in? Like, you can't write a pillar file for that many devices. You can't go configure a supervisor for that many devices. And then if you want to move devices to a different server or container, how does that work? So basically from A to Z, it has to be automated. And so we're going to talk kind of through that whole process about how we go from nothing to getting these minions, these network devices under minion control. So the first step that has to happen is we have to discover these devices. I call it that because we already know some information about the devices. Like we have a source of truth that is Netbox, and anyone probably a lot of you know about that as just a management tool, right? So the sources that feed into that are, of course, the engineers, and we have our own proprietary internal management system. And all we're really pulling from that is a simple list of host names and the data centers that these devices are at. So we're just getting a flat list, or just a dictionary of all the network devices that we have. And there is some extra information in Netbox about the firmware, or what type it is, but we prefer to just have a live discovery, a live dynamic updating discovery, so we can prevent any human error. And so what happens during that discovery is that we pull the list of devices from the Postgres server that we buffer in front of Netbox. Basically, we just have our own Postgres server in our environment, and we're reaching out to each of the devices that we've learned about, and we're going to just query each one, starting with SNMP and falling back to SSH if we can't get the information we need. But we're just gathering stuff about what type of device is it, right? What is it? Is it Arista? Is it a Cisco device? What kind of firmware is it running? And basically, once we gather all that for each device, we actually populate it back into the Postgres. The Postgres database. So we've just discovered certain, there's just a dictionary with certain keys like vendor, OS, firmware, and the IP. And so that's the data gathering effort, and we're building up this our own source of truth as far as the current state of the network and how we want to use that to configure and deploy different types of minions. And so what happens after that is the distribution of those minions into containers. And this is happening at the master of the universe. So we're still at that top tier 1 layer, orchestration layer of the mastership. So we're pulling all the devices from Postgres and basically doing some logic on that dictionary that we pull for each device in order to sort it into a container, basically. So we have native and proxy minion containers, right? And so the distribution into those containers are based on these criteria, which are the vendor, the operating system, and the firmware version. So Python just does some logic on what we see here, and we'll determine where we should. Basically, it's eligibility to run an on-box native minion versus do we have to set up a pillar file and do like a netmiko proxy to that device, right? That's the decision we're making here. And then the data center is something that we can find or infer from the host name, and that's going to kind of help us scope devices to regional servers, right, like Tokyo or Dala 9 here. And so you can see from here, like this is an Arista device. It's running EOS. It's running 4.24.1. So we know it's eligible to be a native minion, right? We can install a native minion on that device. So basically, this whole process runs for each device that we have found. And so like this is a Cisco device. It's a Nexus Cisco device running 824, and we don't yet run on-box minions for that device. So ask David about that if we. So that gets sorted into a proxy minion YAML file, and right here, see, we're still, this is like a physical diagram. Like we're still on the Motu container, the master of the universe container, that top level master. Where all we're doing here is creating flat YAML files, just lists. So this is a really easy way to just take that logic and like all of this device logic and the criteria about the device and just make it, just abstract it out, sort it into lists, and then we'll do something with that later, and you'll see. So what we end up with after the process is complete is a bunch of lists with an expected container name, and this container name is also procedurally generated. So we know kind of where this container is going to live, what type of device it's going to try to run, and this is just a naming scheme that we came up with. But we have all these lists of just host names, file lists of host names after that step. So then what happens after that, after we've generated these allocation files, we're going to a container deployment stage, which is where the salt master on the top level master, the Motu, is going to reach out to a minion on the server. We're not in containers yet here on the server side. We're just going to run a state on that local salt minion that's living on the bare metal server. And I wanted to go through some specific configs here, just specific states, so we can just provide those examples, and maybe something will stick out as interesting, and we can talk about it. But what this is doing is starting the containers first of all, and then doing file.manage for certain things like the master and minion configuration, so that like in the Docker file that we use to build that container, we don't have to manage the configs there. We can manage all of our master and minion configs actually in one repo, and that's great because we'll be using different variables for, if we have 3 containers for a native minion running on one server, they have to have different ports exposed. So those are the kind of variables we're rendering in the master and minion config. And then the allocation file gets file.managed over as well. And then the process starts. So I'll kind of walk through that actually, is the fact that the first thing that happens, we're looping through this also, but we're just starting the container, stopping the salt minion and salt master. And that's important because of the next step, which is that file.managed. And that, so we have to shut down the master and minion process and then put the configs where they need to be and then start the process for that to actually take effect. So and this is also something interesting, the way we did this, the way we decided to do this was when we do the first file.manage, like we're talking to the minion here, right, on the server. We're not able to see into the container just yet, because we don't have a minion running in there that's connected out to the master of the universe. So this is a little tricky, but cool, because file.managed has a template render built in. You can actually render Jinja as you do the file.managed, right? So we have all that, we have the variables in the config file that's in our repo, right, in the Git repo here. And when we do the file.manage, it actually gets printed out into text. And then we can do the Docker copy to have this minion copy the config into the container. Because docker.copy to that module doesn't have a rendering function. So it was kind of cool and interesting. Yeah, and then that allocation file gets copied over. So we have that in the container. And we actually could do Docker copy to like straight from the master to into the container, because we didn't need to render that. It was just that flat YAML file. This is just the list of host names, right? And then we're starting the minion process, and we can do docker.run commands into the container from the salt minion here. And you'll probably notice that a lot of these variables are stripped out. Like there's obviously file source and destination file paths. There's requisites here, but like some of the things that we took out were the includes at the top of the state. Like we're using something to build the Docker bridge network and configure that the way we want to. And so there's a lot more going on, but I wanted this to just be conceptual so that if anything sticks out to anyone, or just like a high level conceptual thing of how you might get this done. And so there's a lot more going on there, but this should be enough to like visualize and maybe come up with your own ideas. And then of course that gets looped, and we use the container name as a variable in each state ID. So this is all happening. That's kind of incorrect. This should actually be a 1. I messed up there, but like we're just iterating through container names, and then that YAML file, like there would be a -1 here, and it would get its file.managed allocation file. So we're using the host names of the container to kind of correlate allocation files as well. And then so this salt proxy toco2 would get file.managed over into a container that had that host name, right? So kind of clever way to do that, I think. After we've done all that, after we've allocated the minions into the container, we start the salt minion. That was the last step here. We're starting the salt minion, and then we actually we use a reactor on that top level master of the universe, right? It's reacting to any minion start event, and it's going to run the state on new container added. And I also have like a short version, a concise version of that state too, to kind of show you what it is. It's a reactor state, and you might be thinking like, why don't we do a startup state? We did actually do a startup state eventually. Like when this minion starts, you can define a startup state in the minion config and get it to just run immediate actions as it starts up. But we didn't have those state runs didn't appear in the event bus, and so it was a little weird, different to troubleshoot from the motif perspective when we're looking at the event bus in that case. And also, I don't know if, just to throw this out there, I don't know if anyone experienced this too, but we got a lot better results just doing reactors, as in more consistent execution. I don't really know if that's an artifact of our situation, but it seemed to be way more performant when we started using reactor states to essentially be the startup states for a salt minion in a container. So yeah, what happens here is we're now just doing another file.manage for data.sls, which is all the pillar data that's common to all devices, right? And that just comes from Vault. I don't think I really illustrated that, but it's literally this file, this data.sls file is just a Vault call. It's like the built-in Vault module in the Salt that just does a Vault call for our whole dictionary of stuff. And that's the information that the container needs to log into the devices, or that like if a proxy minion was deployed here, right, it would look in pillar data to get authentication credentials and stuff. So that's where we get that, and it goes directly into the container. And then of course we're refreshing the pillar, and then starting the salt master. And so what happens here at this point, we're doing some logic based on, I missed a quote there. We're doing some logic based on the container name. So like this container name, like I said, it's used for a couple things, but it's determining, right, if we are going to deploy native minions or proxy minions, right? So if, like as we saw before, anything that was eligible to be a native minion, an on-box running minion, is getting sorted into this native container named native something, right? And so that's what I wanted to focus on mostly here, is the native deployment part. And so basically, if we have a native in that container name, we're just going to run this execution module to install the minions against this allocation file, right? And okay, so this is that process. Basically, this native minion, this native install.py is a Python script that is running on the minion, right? Because we've targeted the minion here. This is a startup state that the minion, or a reactor that the salt minion is running. So this minion is running that code. It's looking at the allocation file. It's going to transfer what is the native minion binary, right? It's something that David actually had a huge hand in developing. He developed it basically with Arista. And so it's this extension that is built for Arista, right? It's literally just .swix. So we copy that over using Netmico to the device that we've already deemed as eligible. We did that logic way before. So we know that all these devices in the allocation file are eligible to run this software. So we're copying it over, we're copying that extension over and installing it, but also there's a bash script that we copy over to. And this is why Arista is great, because we can literally just copy a bash script and run it like from the Linux kernel, and we just, from the CLI even, you do the bash command and pass it some arguments, which are some of the base grains in the minion config, like the fact that it is a native minion or whatever we want to put there. There's some base grains. And then, of course, the IP of the salt master that we want it to connect to. So the salt minion knows that because it's sitting right next to the salt master. It just looks at the config. It just opens the config file and sees what ports that we've chosen to expose and what the local IP is. So we are able to pass that information over into just a simple bash script that writes that config and then starts the Minion process. And then we do we enable the API over Unix sockets, because that Minion is actually talking locally to the device, right? I don't know what I was going to put there. Oh, yeah, it uses the OpenSalt API to run test.ping from the container master. So the Minion right here, to verify that the installation was successful, this salt Minion will actually use a local, like a salt local API call to the salt master to do a test.ping on that device it was just working with to install. And then, so if that comes back successful, we know that was a good install, and we validate that's validated in that way. So we can do, we stuff 2,500 minions in one container, 2,500 native minions, being on device minions, right? And so we can get that installed. This is heavily multi-threaded, and we can install that in less than 10 minutes. We can have a set of 2,500 devices installed in about 10 minutes or less. So it's really, the deploy process for this is really dynamic and quick, and I hope it makes sense in the end, kind of how we got from nothing, right? Just minions on servers to discovering devices, thinking about and building criteria about them, and sorting them into containers, and then performing that installation on all of them. So this is kind of just the logical summary of what I just said, right? The salt minion is grabbing info from Netbox and putting it into Postgres as that buffer and from Netbox. The salt minion in the container, or this is the allocation minion, but let me just flash back to where this actually is. This is basically happening here at the salt minion, in the top level master of the universe. Sorry, I don't want to deviate too much, but this is just kind of the summary. It's of the logic that we're doing. But we're just basically grabbing info from Postgres, doing some logic on it, like we already talked about, deciding if it's proxy or native, and then we're creating that pillar for the authentication details, either starting a proxy process or what I just described was installing and starting that native minion. And so that's the end-to-end. And if I don't know if there were any questions, but that's pretty much what I wanted to talk about. And I hope it was insightful to anyone who's looking to scale or use Docker or anything like that. So I'm happy to also take questions later, and like if you have any more specific things that maybe like how do you do that, or why does this work like that? Yeah, please feel free to put it in the chat. But now, Saeed, I wanted to talk a little bit more about the specific things that we do to those network devices and how we use Salt to orchestrate them. So I'll stop sharing.
Yeah. So you can see my slides right now, right?
Yeah, it looks good.
Okay, so now onto the device side of things and what we do, how we talk to the devices. We use several different methods. First is the proxy minion. The proxy minion is a process that is running inside the container that is also housing the master. The master is using the message bus to talk to the proxy minion. The proxy minion is already running, and it uses whatever method it can use to log into a device and manage it. So in the case of older Arista gear or Cisco IOS, it uses SSH. In case of our Juniper devices, it will use netconf. And basically, the proxy minion is a process per device, and it was developed to be to allow Salt to manage devices that do not allow you to install Minion software, either because it doesn't run on it or you're not allowed to run any software on that device. So it's not an ideal solution. So we only run proxy minions for devices where we have to run proxy minions for. The benefits is, well, we can use Salt to manage those devices, and we can use Salt to manage older or aging operating systems. The disadvantages of running a proxy minion is that it's very resource intensive. So well over 100 megabytes of RAM. It also requires a lot of CPU. So all those processes are continuously running, and if you use the master to target the devices to do something, everything happens in near parallel. And if your master is managing a lot of proxy minions, it basically destroys the CPU of your server. And in addition to that, you have to manage all those processes. We've also noticed that the containers started relatively quickly. The master also starts relatively quickly, but starting a lot of proxy minions is unfortunately a relatively slow process. We've tweaked it a bit, making the proxy minion use the local file system. So after startup, they don't have to use the message bus to copy all the files over, all the execution modules and custom states, etc. But still, you're looking at, I don't know, 10 to 15 minutes before everything is ready to go and quieted down. We are now also starting to use the Delta proxy. So basically, the Delta proxy is a single proxy minion process, or a single minion process that is running in the same container that is housing the master. The master uses the message bus to run or to instruct the Delta proxy what to do. And instead of having a relation with one other device, and instead of having a Delta proxy per device, we now have, instead of having a proxy minion per device, we now have a Delta proxy for up to 100 devices. So the advantages are I think pretty clear. Instead of having 100 processes consume over 100 megabytes of RAM, we have one process that consumes that memory. The disadvantages currently, at least, are that the first iteration of the Delta proxy only supports NetMiko, and that concurrent operations are still heavy on the CPU. So if you target all the devices that the Delta proxy is managing right now at the same time, then it's quite taxing for the server that is running this process. I should also note that if you're used to working with proxy minions, then pretty much everything that you're used to using with the proxy minion is also available using the Delta proxy. So a pillar is rendered for every device managed by the Delta proxy, and there are grains for every device, and pretty much the way you work with your execution modules or the way you work with your custom states, all that stays the same. You'll just be able to control a lot more devices using a lot less memory. The next best thing, or really the best thing, when you're working with Salt, is to use a Salt minion. With the latest developments from Salt are that the Salt minion has been created and delivered for Arista and Juniper. We've been using it for Arista. We're still looking into using it on the Juniper devices, but for the Aristas, we've been using it for quite some time now. And so what it looks like is the Salt master is using the message bus to communicate with a minion that is running on the Arista device, and the minion will communicate with the E API, or in our case, we turn up the E API, and the minion will communicate with the E API to control the device. And the whole development was a joint effort between Salt and the vendor, between Salt and Arista. And the end result was that the minion is delivered as a binary. So basically, you can upload it to the Arista device, and you can run it as a process. So you can also upgrade the one or the other. So if there is a bug or if there's some issue in a version of EOS, you can upgrade that without having to upgrade the minion. And otherwise, if you want to upgrade the Salt minion on the Arista, you don't have to reinstall or upgrade EOS on the device. Also, if you're running 4.18 or above, you don't have to reinstall EOS. It's just good to go. So the advantages are clearly not having to run any proxy minion or delta proxy. In our case, we only need to run a salt master in a container. And instead of controlling a few hundred devices, we control thousands of devices. And everything is just a lot more responsive, because if you target devices and want something to be done immediately, then all the minions will execute it in near parallel. And because they're not touching the CPUs on the server, they're all just executing it very quickly. And the server almost immediately gets the response of all those minions at the same time. The salt minion is also just running as an independent process on the device. And whenever the connectivity to the master is lost, the minion just keeps on running and doing its thing. So if there is a salt state or an execution module that you're running that disrupts service, or that you want to use to reset a line card or a few BGP sessions, then it can just continue doing its thing. And after it's done, it can post its results back to the message bus. Now, if you have a proxy minion, then you're dependent on the connectivity from the proxy minion process to the device. And if you lose the connectivity from the proxy minion to the device, you have a problem. The commands are also executed a lot faster. If you, for instance, run a proxy minion on a server somewhere in let's say, Dallas, and you're managing a device in Washington or maybe Tokyo, then you're writing and reading from an SSH channel if you're using SSH to manage a device. And then every subsequent command you issue, or every subsequent command that the proxy minion issues, you have to wait for the previous command to return. And also with an API, you can make the one API call after the other, but still you have to continuously wait for a return. If you have longer states, things just become slow. With the minion running on the same CPU as basically the minion running on the CPU of the device, everything is just very quickly. The master just issues the job through the message bus. The minion picks it up, and then it starts executing it. And only when it's done does it return the result to the master. So managing devices that are located far away from your server is less of a problem. There are still some disadvantages, I think, or some things that you have to be mindful of, especially if you're used to using proxy minions. So there's less CPU or memory typically available on networking devices. So you need to be aware of that. There are some restrictions or securities built into the salt minion. So as soon as it starts to use more than, I think, 200 megabytes of RAM, then it will just restart itself. So there's a hard limit on that to safeguard the device. But if you cannot go too wild in your execution modules, so to speak. And also there are some limitations to the packages that you can use. So instead of being able to pip install whatever you can find, you'll have to be careful or be aware of maybe relying on some C library somewhere that you just cannot use on the Arista. So, like Nate described earlier, we kind of settled on currently 2,500 minions being controlled by a single master. I think we can, after maybe some more investigation, we can push it a bit further than that. But right now, it's at 2,500, and here you can see. Giving or issuing a command targeting all the Arista devices managed by this master, and then just doing a show version command. And if we do this, then typically all the devices respond to the master within 10 seconds, or somewhere around 10 seconds. Never been able to do that just using Python with threading or whatever technique. And I think it's a phenomenal improvement, and it makes it very easy to talk to a great number of devices. So we run multiple masters on a server, and making a few API calls to different containers that are housing these masters, then it becomes relatively easy to instruct a great many number of devices to do something for you. So I wanted to touch on two things that we do with the we do it with the proxy minions and with the native minions, but the native minions just make it a lot easier. So we periodically we do a lot of data gathering, and we periodically gather data for all our devices. We have a state that is scheduled to run periodically, and what happens is the minion process communicates with the eAPI, and it gathers a lot of information from the device. So this information is with regards to, or this information includes all the line cards, the optics, the serials, the software version, all the LDP neighbors to be able to build and understand the topology, all the possible interface information, and also a configuration file. The minion then, after it's done collecting this data and writing it to its local file system, copies it over to the master. So then it becomes, then it sits in the file system of the container. And there we have that minion that is managing the container. This minion also has a schedule, and periodically it takes all the files from in case it's a native minion container, it takes all the files of the 2,500 devices, and it sends that data to SSOT, which is our system, or the name for our system that is the single source of truth for everything. So all our masters do the same thing, and this is how we can fill the database and build our view of the network. Now, in addition to using the minion for data gathering and running arbitrary commands, we can also use it for device configuration. The way we do it right now is we leverage the eAPI. The native minion, or the salt minion that runs on the Arista, comes with Napalm. So it also comes with all the libraries that Napalm uses or relies on. One of those libraries is PyAPI, which is the thing that we mostly use. On the device, we configure, obviously, the eAPI, and we allow communication with the eAPI over Unix sockets. That way, we don't even have to expose the API to the rest of the network. And whenever we are configuring a device, we use configuration sessions. This allows us to observe a change impact prior to the actual change. We can retrieve a diff. We're ensured that we can configure all the configuration, like we can configure every single line of an access list and then commit at the end, and not worry about only applying half, like you typically have to worry about when you're configuring something on a Cisco IOS router, for instance. And you also have the availability to use a commit timer, so you can commit the configuration and then use the timer, and then a little while later, if everything is still okay, you can commit a second time to make it permanent. The configuration generation part is done using different sources of data. So the minion that is running on the device renders the configuration, and when it is building the configuration, it uses pillar grains and map files. So the pillar is kept small, since we're managing a large number of devices, and the master is continuously having to render the pillar for all those devices. We only put secrets or sensitive information in the pillar. We had in the very beginning once put all our server IPs and all the data that describes our network and data centers into the pillar, and the pillar blew up to several hundred thousands of lines, and it just crushes your master's capability to basically do anything. So we kept it extremely small. The pillar is now extremely small, and when we render a template, we can access all the secrets and SNMP or usernames, etc. The grains we use for properties of the individual device. So we periodically run custom execution modules to set grains that will describe the software version of the device and several other things we think are important. And then the map files, which are files that are contain JSON or YAML or Jinja. They are built using the minion that is running in the container. And they're put in the file system of the container. And during the rendering phase, the minion that is running on the device, being controlled by that master, can also access those very same map files. So the larger data sets that we have, we put them in map files. So we can still access all the IP addresses or whatever information that describes our network, but we don't have to leverage the pillar for that. So this is an example template. This is not an actual template, but this is how a few things that we do, how they can look. So here you can see at the top, we retrieve the SNMP community from Pillar. I think that's a sensitive piece of information, and then we generate the configuration line for it. Here we retrieve grains like the software version, and then you can test if your software version is in a certain list, that you can send some specific command that is relevant for that software release. And if you have a map file that includes a JSON data, then you can import it like this. And here in this example, I retrieve the role and the data center as grains. And then I use the data center grain to do a lookup in the map file, retrieve the autonomous system, and then I can use the autonomous system in the template, basically. The configuration of the device. So we use the E API, we use Pi API. We want to control the exact behavior of everything. So what we do is we have states, and the states execute a certain amount of state IDs. Every state ID is a custom state where we have the higher level logic, and every custom state runs one or more execution modules, which are like lower level or very specific functions. And we control what states get executed by using requisites. Requisites basically allow you to say, okay, I only want to execute state ID Y if state ID X shows changes or returns false. So how does this look? In our case, this is an example of a configuration state. So first we do a remediate check. Basically, we test load the configuration to see if there are any changes. And then only if there would be any changes, then we continue with the next step. So here the requisite is on changes, remediate check. Then we save the configuration. Then we run some health checks, like are the uplinks up, or is BGP still functioning, or is there anything we should worry about? If there's something we should worry about, we return false and we abort. If there isn't anything we should worry about, we make a pre-change snapshot. In the pre-change snapshot, we capture a lot of state of the device. So could be the number of BGP peers that are active on the device, or the number of OSPF sessions, the number of interfaces that are up, etc. We write that to a local file system. Then we open a configuration session, render the template, apply the configuration commands, do a commit with the timer, run the post-change snapshot. Basically, we capture the exact same state of the device. We do a comparison with the information that we gathered prior to making the change. And then we can decide, if there's a failure in any of the post-change checks, then we can do a rollback. If there are no failures, then we save the configuration and we move on. So a short summary. Nate started off describing the infrastructure. So high level, focusing on the salt containers that actually manage the devices. We have a Motu container housing a master. This master is controlling salt minions that controls that are controlling the servers and the containers. The Motu containers have access to Vault, which allows the salt minion to pull in the secrets and build the pillar files. The salt minions also have access to SSOT to build all the other files required to understand whether or not we should run proxies, whether or not we should run native minions, and also gather the map files and all the other pieces of information we require. The master that is running inside the salt container is talking to a Delta proxy or a proxy minion that is a process that is also running in the same container, or it is talking to a salt minion, which is a process that is running on the network device, currently mainly or only the Arista native minion. In the future, we're looking to integrate the Juniper native minion as well. Other applications can also use Salt by talking to the API, and GitHub is periodically downloaded into every container so that we continuously have access to the latest and greatest in our own code base. That was a summary, and I don't know, you have anything to add, Nate, before we maybe move on to questions?
No, that was awesome.
So you guys, I'm going to kind of play back through a couple of questions in the chat. Just a couple of little clarifications. There were some questions as to the status of Arista, for example. From Salt's perspective, Arista is a first-party vendor, and as a result, the native minion that we build and package with their help, we have the fortune to have David Murphy packaging Salt for us to consume on any number of different platforms. Arista happens to be one of those, and they actually certify and bless those Swix packages, but ultimately they're available through us. And in terms of what that looks like in terms of how to acquire the Arista or the Juniper native minion, those will be available from SaltStack's enterprise site, pretty much the same way that we would do for something like the WinRM package or the AIX or Solaris minions and things of that nature. So that mechanism works very much the same way. It will appear on the downloads page and be available for people who have existing Zendesk accounts.
Yeah, maybe an important addition is that even though it's found underneath the underneath SSE or on that download page, it works exactly the same, or you can work with it in exactly the same way as you work with a proxy minion or a normal regular Salt minion. So there's no change when you move to incorporate that into your environment. Right. Nothing to get used to, so to speak.
Yeah, and one of the interesting things, and I think a lot of this will impact a lot of network use cases, is that essentially SaltStack Enterprise itself doesn't change the way that Salt minions interact with their masters. It's really essentially a management layer on top. So a lot of the functionality in terms of how we interact with individual native minions and things like that is unaffected by the actual presence or absence of SaltStack Enterprise itself. It really comes down to the minion to master communication. The next question that we had was regarding, sorry, kind of lost it here in the mix. The selection of using a Salt master directly from Motu rather than using Salt Syndic. And by all means, Saeed and Nate, correct me if I'm wrong, but part of that consideration is the existence of SaltStack Enterprise in the environment. Essentially, the idea is less to try to be able to transmit instructions across all of the different masters to the individual devices. That's certainly an element of it. But the existence of masters of the universe is essentially to handle the management plane of the container hosts that are spinning up the individual Salt masters as well as all of the proxy minions. So essentially it's an out-of-band management for the infrastructure itself.
Yeah, that's a good way to describe it. And we did look at a syndic masters, that kind of setup, and I think Gary didn't have that much confidence in it either, and we were already pushing towards SaltStack Enterprise. So.
Another limitation.
We also have we have all the devices in our database. So if we lose a container or a server, then we can periodically reallocate devices and schedule them out across our containers. So it's not really, that is kind of self-managing or self-healing, I think you could also call it.
Absolutely. There's also a practical limitation of Salt Syndic in the neighborhood of about 120 masters. And to my understanding, your guys' implementation still exceeds that. So that's another consideration there in terms of whether or not Salt Syndic would even be practically applicable. Just kind of looking, we have about 3 minutes left. I just want to make sure that we answer these and then get on to any of the other questions. In terms of, from Gary Geeson, are you using regular proxy minion or Delta proxy? There's a mix. Nathan answered that pretty well in chat. They have about 15,000 minions currently using Delta proxy, but they're limited currently to minions that rely on NetMiko, so primarily the Cisco part of the infrastructure right now. Delta proxy is, that's interesting. So Delta proxy also right now, so it is available with SaltStack Enterprise 6.4 and the, whichever element we're on now. Sorry, Salt 3002. I just know the numbers. I don't do code names because I'm not on the engineering side anymore. So magnesium, I think, is that right? And so it is available, but at least at the outset, because of its status, it's available kind of in much the same vein alongside SaltStack Enterprise. I can't speak to roadmap, although you can jump on Alex Pay's session later if you want to talk about whether or not it will become available in open, whether or not that applies. In terms of minion master communication, I'm sorry, I'm skipping one here. IBM's implementation is a highly heterogeneous environment, many different firmware versions, many different vendors. And so that's ultimately one of the reasons that SALT came up as the solution of choice for management, just because the desire to be able to control all of these things from a single management backplane rather than having to mix and match Cisco ACI and Juniper Enterprise and all of those things would have turned into a, I'm not going to say unmanageable, but certainly would add a level of complexity that was considered unacceptable, I think, in the use case there.
Yeah.
The amount of traffic, SALT itself, the individual masters don't contact any of the devices directly. Ultimately, in the case of something like a native minion, it will contact, just because of the pull model, the native minion will load the Python libraries to make SALT happen, and it will reach the SALT master directly. In cases of anything using SALT proxy or Delta proxy, there is a proxy process that becomes responsible for contacting the SALT master and then retrieving any of those instruction sets and then selectively passing on and as well as handling language translation. So if you're going to talk to a Juniper device, then it'll do netconf over SSH on port 830 from the SALT proxy process to the device itself. So the amount of overall traffic is kind of tunable to what you're doing. In this case with IBM, you guys are running with persistent connections off, so they will reinitiate connections when they're needed rather than attempting to keep those SSH sessions open.
Yeah, so there's really no traffic towards a network device unless you actually issue something in the case of a proxy minion. And then in native minions, interesting to mention, like we worked with David to put like Linux ulimit type like memory limits and CPU kind of hard limits that are methods of protection for that process running on the Arista device. So we've tested that thoroughly, and that's something interesting about the Arista native minion. We found it to be very performant and safe.
Yeah, and also back to what Patrick just said, like the proxy minion translating things and then doing SSH or netconf to the device. If you move to use the minion and run it on an Arista device, obviously the interfaces into Arista are still the same. So if you want to do CLI, then you can do command.run and basically call, I think the fast CLI is what it's called. But if you're if you're accustomed to using the eAPI, you can use PyAPI or Napalm and communicate with the eAPI. And also, the latest versions of Arista have some limited support, some support for netconf as well. And since Napalm also supports the PyEZ library to talk to Juniper devices, it's also shipped with the NC client, so you can also write your own custom execution models to do netconf with the device, or write something yourself to do GNMI, which is also supported on the Arista in the latest versions. You're not the native minion is not going to magically do the translation for you. So you're still interfacing with the device. It's just that you're not running a proxy minion process. It's run on the device, and that just makes your instance of Salt a lot more powerful.
I know that we're a couple of minutes over, you guys, so I don't know. I assume the platform will close this session momentarily, but I do want to call everybody's attention to the fact that the Expo Hall is open for virtual booth attendance, or by all means, I'm on Pacific time, so I'm about to take a lunch break. And thank you all for attending. If you have any other questions, by all means, surface those to us, either directly to me, and I can make sure that those questions make their way to Saeed or Nate, or you can use the direct message function to talk to them, or by all means contact a Salt marketing or salesperson, and we can obviously direct all of those things together. We're integrating into VMware, but we're not invisibly so yet. So by all means, we can track each other down and make sure that the messages make it to the right place. Thanks, everybody.
Yeah, absolutely. Thank you guys for coming. Appreciate
Thank you.